Hello students, we're going to talk about 3.4 today. This is the start of writing proofs. So the basics of it all is what we're going to cover. We will spend plenty of time practicing how to do them. So the first thing they put in proofs is just the postulates or axioms that are about points, lines, and planes. Accepted as true without proof is what a postulate is. Postulates listed below are about points, lines, and planes. Cannot be proven, but we do assume them to be true in order to do proofs. So you can take your time to look at these, but through any 2 points, there's exactly one line. So essentially the idea there is that if you have any 2 points, oh, that's really big. Hold on a second. So if you have a point and a point, there is exactly one line that I can draw through those 2 points. That's what that postulate is saying. Through any 3 non-collinear points, there's exactly one plane. So if I have 3 non-collinear points, there's exactly one plane that I can put through all 3 of those points. And for those points that I just drew there, that would be the screen. Okay. A line contains at least 2 points. So this is saying that if I have a line, that line contains at least 2 points. There's no way else to have a line. You can't have 1 point. A plane contains at least 3 non-collinear points. So if you have a plane, in this case, it's saying that that plane contains at least 3 non-collinear points. That's how a plane has to be made up. If 2 points lie in a plane, so you have a plane and you have 2 points that lie in that plane, then the entire line containing those points lies in that plane. So if you imagine drawing a line through that, even though you could draw it beyond it, okay, remember that lines go on forever and planes go on forever. So this plane extends in every direction. And so what this postulate is saying is that that entire line is in that plane. If 2 lines intersect, so we have 2 lines that intersect, you can draw them lots of different ways, then their intersection is exactly 1 point. No matter what, no matter how you do it, they intersect in exactly 1 point. And if 2 planes intersect, so we have a plane that intersects, and we'll just draw the other plane off to the side here, kind of think about like the side of a box, they intersect in exactly 1 line. Remember, these are just representations of the plane, and that line is just a representation of that line. They go on forever. Okay, so you can look through those, think about those, but you're just going to want to know that those exist. A lot of what you're going to do with those is just determine always, sometimes, or never. So it's just more understanding and just thinking through them. So 2 intersecting lines determine a plane is your first one that's given to you. So if you think through that idea of sometimes, always, or never, the answer to this is always. Okay, so 2 intersecting lines. So you intersect like this. You can't have parallel lines. We could have, like, we could talk about in a plane, we have a line, and then you could draw a line that's intersecting through here or whatever. Like, those are 2 intersecting lines. But no matter what, when you draw 2 intersecting lines, they always determine a plane. Okay. Over here, that plane is just the screen. Okay. Over here, even though there's a plane shown here, there is a plane that contains these lines. That plane just happens to be not the one that is drawn. Okay, so that's what's giving there. You can talk through lots of different things with that, but just thinking about those always, sometimes, or never. Off to the side, there's another statement. Through any 3 points, there is exactly 1 plane. So think about that. Through any 3 points, so we could have 3 points here. Okay, there's exactly 1 plane. Yes, there is 1 plane through those 3 points that is there. But through any 3 points means that those 3 points could be collinear. And if they are collinear, there is a plane that exists this direction, but then there's also, if you imagine that kind of the axis of rotation, there's a plane that can be kind of that direction. So imagine that first one I drew vertical, this one I drew horizontal, and many other planes. Okay, so there, that is not true. So this one would be just, is this a true statement? No, to answer that question. Okay, so now that takes us to proofs. So we're going to talk about a lot of stuff with proofs. So proof is just a logical argument in which each statement is supported by a statement that is accepted as true. So we're going to have what are considered statements, and then we are going to have what are considered reasons for each of those statements. So as we go, we will talk about a lot of different ways to prove, but 2-column proof tends to be kind of the go-to way to do it. We're going to talk about 2-column proof, we're going to talk about paragraph proof, and we're going to talk about flow proof. And all of those are viable options. It's just good to know that you have different options. I have a lot of students that like two-column proof. I have some students that like the flow proofs. Okay, most people don't usually go to paragraph proof if they don't have to. But you can develop a deductive argument to prove a statement by logical reasons, chains of statements and reasons. Don't worry about what a deductive argument is. Same thing as inductive reasoning and deductive reasoning. I'm not worried about that idea. We just want to be able to reason. Okay, so we're going to start with two-column proofs. We're going to get to paragraph proofs. We're going to do flow proofs. No matter what, if I get to ask you to give me a proof, you can give me any one of them. So if it says give me a paragraph proof, you can put it in whatever format you want. Okay, so that's something to know going forward. The steps to a good proof, though, no matter what way you do it, are these. Okay, you list the given information. So you're going to have something that says given, and it's going to list some information. You're going to draw a diagram if you need it. So maybe there's a triangle or whatever. You're going to draw a diagram. Okay, you're going to create a deductive argument that links the given information to the statement that you are proving. So you're going to start listing things. If you're doing a two-column proof, you're going to make a statement. You're going to make a reason. You're going to make a statement. You're going to make a reason. You're going to kind of do it in that order. Okay. You're going to justify each statement with a reason. So the statements is step 2, the reasons are step 3 kind of there, but usually you're going to go back and forth. So you're going to do statement and then reason and then statement and then reason. Okay. And then you have to state what you have proven. So in the end, the last idea, so you're going to do given and prove, is that you're going to actually state whatever that prove is going to be your last statement down here. Now you're not going to write prove. So we're going to go through some examples so that you can see what that looks like here. Example 3 in your book, so we're on page 182, I believe, keeping up with my book here, gives you a complete the blanks here. So complete the two-column proof by selecting the correct statements and reasons. They give you options on the left. I'm going to kind of ignore those and just go through them. Okay. So they give you a given right here, good proof. Q is the midpoint of PR. So if I come over to the diagram here, and they've given you a diagram there, but I know that Q is the midpoint of PR. So that is given to me. Notice I did not mark my congruence in here because when you do a proof, marking those as congruence is actually another thing. It doesn't say that PQ is congruent to QR. Okay, it says Q is the midpoint of PR. And if you notice, we're actually proving that PQ is congruent to QR. So do we know that? Yes, we know that. We go through our steps to do it. So the Q is the midpoint of PR is what leads us to being able to say that PQ is equal to QR. Now, PQ equal to QR there is what we can say, and this is by the definition of a midpoint. Now, your definitions, remember, are all biconditionals. This definition says if you have a midpoint, okay, then it splits the segment into 2 equal parts. Now, because, actually, let me finish this and I'll talk about that. So definition of midpoint. And then, so we were able to go from step 1 to step 2. Now we want to go from step 2 to step 3. If you know that PQ is equal to QR, you can say that segment PQ is congruent to segment QR by the definition of congruence. Now, the definition of congruence essentially says that if there's 2 equal parts, then there are 2 congruent parts. Okay. Now, because the definition of congruence is kind of one of those things in geometry that we use interchangeably. So equal and congruent, we state it the correct way, but we're going to use it interchangeably. In this proof, if you had done this just in 2 steps, you did the given, and then you said PQ is congruent to QR by the definition of midpoint, I would take that because essentially what you're doing is understanding that if a midpoint, then it splits it into 2 congruent parts is really the same thing as 2 equal parts. Okay, we'll get into some of that. We'll use more examples. We'll talk about it a lot more to understand that. But that's the way that the book has done it, and that's kind of what we can do from there. So what you're going to see right below this is that what we just proved is the midpoint theorem. So the midpoint theorem says if M is the midpoint of AB, then AM is congruent to MB. So we proved if we have a midpoint, we can say congruence. I say use the midpoint theorem or the definition of midpoint interchangeably. They really say pretty much the same thing. This doesn't happen a ton in geometry, but these 2 things say the same thing. So we do use these interchangeably. Okay, so I don't care if you state congruence or equality out of either one of those. You can use them interchangeably as we go. Okay, so look at another proof. My suggestion, try this. Pause the video, try it. Okay, and then come back to this video and see how you did with it. So they give you the given. B is the midpoint of AC. They've listed that. C is the midpoint of DE. They've listed that, and they have the given. Now, if you notice, there's one more given statement, and they don't list that until down here, and they have the given. This is kind of a strategy that people use in proofs, is they list a statement, and then they use that statement, and then they list another given, and they use that statement, and lead to the end. You can list all your given at the beginning, or you can wait, kind of like they did there. Okay, so B is the midpoint of AC and C is the midpoint of DE, leads us to being able to say something. Okay, we have the midpoint word used. If you're using a word in this, you're almost always using a definition. So you can see they're using the definition of midpoint to state something. Now, what you're going to state here, so if B is the midpoint of AC, is you're going to state that AB, the measure between A and B, is equal to the distance between B and C, which is BC. Okay, and if C is the midpoint of DE, then I can look here and I should be able to state that those distances are the same, so that DC is equal to CE. So those are my two pieces that are given, or that are out of the definition of midpoint. So again, I was able to go from step 1 to step 2 by using the definition of midpoint. If there is a midpoint, then the measures are equal. Okay, now step 3 actually comes just back from the given. So I'm not going from step 2 to step 3. I'm not connecting the dots here. I'm going to connect step 3 to step 4. And I'm actually going to connect both step 2 and step 3 to step 4 in order to get to this. So step 4 is going to say that BC is equal to DC. I put the wrong one. BC is equal to CE is what we're going to say here. I'm going to get this over here, sorry. And this is going to be by substitution. So you guys are going to use substitution a lot. If you are going to abbreviate substitution, do not use SUB, because we're also going to use subtraction. So at least go to the S. I don't know, I always go to the T, so up to you. But BC is equal to CE. So let's talk about the substitution. So what is happening here, and anytime you use substitution, you should be able to circle something and arrow it to something else. So I should be able to see in this case that I got to follow it here. I took BC from here, which was equal to AB, and I replaced the AB down here with the BC. Okay, so if I take that BC and I put it on top of the AB, I would have BC equal to CE, which is exactly what I wrote down here. So I took the BC and I substituted it in for the AB. That's substitution property. Okay, now I'm going to do that again. So I'm going to change my colors here because it says substitution again. I used this statement in this one, so I'm likely going to use this one over here now. And that's exactly what I'm going to do. I'm going to take this DC, since it's equal to CE, and I'm going to substitute it in for the CE. And so then it would read BC is equal to DC, which is what I wrote down here. So we're using that substitution property in order to substitute amounts in for something else, okay? When you use substitution, you should always be able to, if you're using it incorrectly, I'm going to ask you the question of what did you take and where did you put it? And you should always be able to circle what you took and show me with an arrow where you put it. And those two statements should be written down. If they're not, then you're missing something for substitution. Okay, so that's the idea there. Now, flow proofs use boxes and arrows to show the logical progression. Some of you will like this because there will be different parts to it. So I'm going to come back to this one real quick. Like in this flow proof, you would have had a box that did step 1 with the reason, and it would have led to step 2. And then you would have had another box that had step 3 as a reason. And then those two, step 2 and step 3, would have led to like a step 4, kind of that idea. And then your step I got to remember what it was. Your step 2 and your step 4 went together to lead to step 5. So if you kind of like that organization, you can go into flow proofs instead. So let's look at this flow proof here. Flow proof here. So given P is the midpoint of JK. So the first thing we should see is that. So P is the midpoint of JK, and there's my reason is given. You write the reason right below the box. Okay. So if P is the midpoint of JK, then I'm able to lead to the fact that JP, segment JP, is congruent to segment PK in this one. And I'm able to do that by the midpoint theorem. So we can say the midpoint theorem here. And then they use the definition of congruence to state that JP was equal to PK. Now, what I said earlier, let's see if we follow this, is that essentially I can combine these two steps. And if I were to skip over this step and to go straight from stating a midpoint down to here, then my answer here would be the midpoint theorem or the definition of midpoint. Either one of those is fine to use here. Okay. And most of you are going to make this step. So that's why I'm going to cross that out and show that to you guys. Okay. So we can go straight from midpoint to, I need to say that they're equal to each other in this case. And I need to say they're equal because I'm going to be using their measurements. Okay. So the next thing that I want to say here is that, so let's see what else we're given. We're given that JP is equal to X. And actually, we should have that back up here in the given. We should have that JP is equal to X, and we should have that PK is equal to 5X minus 8. Those are given in the diagram, which is also a given statement there. So what I can do now is I can take this JP, let me change my color here. I can take this X that's right here for JP, and I can substitute it in for JP. And then I can take this 5X minus 8 that's right here for PK, and I can substitute it in. So we're going to do a substitution and say that X is equal to 5X minus 8. And again, that was substitution that we were doing there. So we have that step there. From here, we're going to start to solve. Now, this is going to use your algebra skills right here. So we're going to start to solve, and we're going to use subtraction property. So what you're going to see here is subtraction property says you can take the same quantity away from both sides of an equation. So you're going to see subtract 5x and subtract 5x on both sides. And all it is it's a recopy of this step down here, but with minus 5x on both sides. So you subtract. Okay. And then once you do subtraction property, your next step, you can either call it substitution or simplify, but your next step is a simplification here. Okay, so we have to do substitution or simplify to get to this step, which is just really that x minus 5x is negative 4x and 5x minus 5x cancels out. And then you do the division property, so you can see that they're dividing both sides by negative 4 to get to the fact that x is equal to 2. Again, that would be a simplify step. We'll talk a little bit more in depth about the different steps in here more later. You have another flow proof that you can do and you can practice with. It's the same idea as that one, so we're going to skip over that one for now. And we're going to talk paragraph proof. So another way to do it is in paragraph. Most of you will skip this, and I actually tend to skip it because I don't think it does a good job of pairing the statement and the reason very well. But you can look through this. Anytime your textbook asks for a paragraph proof, you can choose to give me either one of the other proofs. Okay, and I will not give you anything in paragraph form. So again, you have a check on that one that you could potentially do if you wanted to. Last but not least, there's the properties of equality that are in here: reflexive, symmetric, and transitive. We're going to use these at different times. Reflexive property of equality will not come up probably until we get into triangle congruence, and we'll talk about when we need that. But essentially the idea is that if we have these two triangles and we're trying to say that they're congruent, you have to be able to say that this side of triangle 1 is congruent to this side of triangle 2, and it's the same side. So that's why you would say that one thing is equal to itself. Symmetric property is really the idea that if, like, when you're solving a problem and you solve and you get that 2 is equal to x, that you can write that x is equal to 2. Most of you will do this without even thinking about it, but in proof, we're going to show, like, hey, I can switch this around using symmetric property. And then transitive property is going to come up at times. It's very similar to substitution, but if we're able to say that, you know, x is equal to b and b is equal to 3, then I know from this that x is equal to 3. That's using the transitive property. In this case, it's also substitution. Sometimes substitution is transitive, sometimes transitive is substitution, and sometimes they're not. So we're going to get more in depth into that as well. So that's what I have for you today.